So, now we are going to see some of the millimeter wave applications which are already in use. So, the first one is in scientific research in space applications. So, we know that these galaxies, stars, they emits electromagnetic waves. So, starting from gamma rays, X rays, optical wave to even at millimeter wave frequencies. So, already we have imaging systems at optical wave frequencies, at X ray frequencies. So, we can gather more information. So, if we have some imaging system at millimeter wave frequencies. So, that is why already different space based imager is there at millimeter wave frequencies, at submillimeter wave frequencies, even at terahertz frequencies. So, which basically take images of different galaxies and stars, and we can extract information from these images, more information which may not be available at optical frequencies. So, for example, galactic dust, it attenuates optical frequency X rays, but the attenuation of millimeter wave frequencies compared to the optical frequencies is much smaller by this galactic dust. So, then if we form any image at millimeter wave frequencies, we can have more information about the galaxies. So, that is why imaging at millimeter wave frequencies is very popular, but one problem we face when we go for millimeter wave imaging, this is the atmospheric attenuation. So, that is why ground based imaging, which we called radio astronomy basically. So, it is not very popular at millimeter wave frequencies. So, we have to send this imaging or receiver in orbit, and all these imaging systems are satellite based. So, in Hubble Space Telescope, in Kepler's mission, already they are being used, not only at millimeter wave frequencies, even at terahertz frequencies. So, here one example. So, this photograph, it is taken at millimeter wave frequencies. You can see the different stars here, and not only that, the galactic dust is also visible here. So, there was one millimeter wave array on Earth, it is popularly known as CARMAD array, and typical frequency range it used 1 centimeter and 3 millimeter, and it consists of 23 parabolic reflector antennas. It is quite big, and it was maintained by California Institute of Technology, but right now it is not in working condition. So, we could actually take image from ground based system by using this large aperture arrays, and we could gather many information by using this millimeter wave imaging systems. So, not only for radio astronomy, we can also measure the upper atmospheric temperature at 60 gigahertz. Oxygen molecules, they emits radiation, and which is a function of temperature and pressure. So, by noting down the emission from this upper atmosphere, we can determine the temperature. Some other applications in telecommunication, they are already being used by different satellite systems. So, at millimeter wave frequencies, we can generate pencil like beam. So, close proximity to one another without causing any interference is possible. Point to point communication is possible. So, as we have seen that millimeter wave we can use for line of sight communication. So, then from one satellite to another satellite link, we can easily design at millimeter wave frequencies. So, it can be a replacement or supplement to fiber optics. So, for example, 38.6 to 40 gigahertz band, it is already being used for high speed microwave data link. So, as high as 25 Gbps. There are some more bands already in use for point to point and high bandwidth communication links like 71 to 76 gigahertz, 81 to 86 gigahertz and 92 to 95 gigahertz. So, now scientists are trying to increase the data throughput and as high as 10 Gbps, and already some of the university groups they designed this 10 Gbps link recently. So, upcoming Wi-Fi standard, for example, IEEE 802.11 AD will run on the 60 gigahertz typical data transfer rate up to 7 Gbps. So, one advantage with this millimeter wave, we see that secure data link is easily possible. So, that is why it is also popular in defense application. So, how this secure data link is possible? Because we can easily generate pencil like beam. So, we can send the electromagnetic signal to my desired direction and no other people will get the electromagnetic signal. So, we do not need coding or anything. So, I will just send my pencil like beam to the desired receiver in desired direction. So, that is how secure data link is possible using pencil beam. Some other applications, passive imaging. So, what is the difference between passive imaging and active imaging? In active imaging, we use some sort of transmitter. So, for example, in remote sensing, so satellites they carry some transmitter which continuously generate microwave or millimeter wave pulses, and this pulse illuminate the objects, and then we can see this object by using receiver part of the radar. So, this is called the active imaging. In passive imaging, we do not use any transmitter. So, due to black body radiation, all objects they radiate some sort of power, and the power spectrum it is a function of the temperature of that particular object and the emissivity of that particular object. So, we can utilize the emission by these objects without illuminating them. So, this is called passive imaging. So, the advantage of passive imaging, you do not have to illuminate the object. So, you do not know the you are being imaging by some other persons or not. So, this is then very useful for security application. So, now for when we deal with passive imaging, we deal with several factors. So, two among these two are, so what is the emissivity of any object and what is the reflectivity of any object. So, when any other signal from any other source falls on any body, it will reflect that signal. It also happens at millimeter wave frequencies, and reflection will be higher if the reflectivity of the object is higher. So, for example, metal it is a good reflector. So, if anything falls on metal, then it will reflect that power. So, why reflectivity is important at passive imaging? Because the outer atmosphere it has some finite temperature and it is also radiating electromagnetic signal. So, this electromagnetic signal it is constantly illuminating the objects in outdoor scenario, and then we call it actually the dwelling radiation, and this dwelling radiation is reflected by different types of objects. So, then for passive imaging we see that basically we have two different sources. One is due to the reflected wave due to this dwelling radiation, and the second one is the black body radiation, which depends on the emissivity of that particular object and the physical temperature of that particular object. So, now effective radiometric temperature of any object T E, it comprises of two components given as T S and T S C. So, this T S, we call it the surface brightness temperature. It actually due to the black body radiation, and it is equal to the physical temperature of the body, let us say T naught, multiplied by emissivity of that object. And the second term, this is the scattered radiometric temperature. So, this is it represents the reflection by object, and this is equal to reflectivity rho multiplied by radiometric temperature T illumination. Now, if I go through different values for the effective emissivity of different materials, we see that emissivity, it varies with material. Not only that, emissivity, it is also a function of frequency. For example, bare metal, it has an emissivity of 0.01 at 44 gigahertz, and it increases to 0.06 at 140 gigahertz. And now, if you go through the table, then for the rough or hard packed dirt, so it is a very good emitter. Emissivity is 1 at 44 gigahertz, at 94 gigahertz, even at 140 gigahertz. So, if I consider that transmission through the medium is almost 0. So, in that case, emissivity plus reflectivity, that is equal to 1. So, for bare metal, then the emissivity is given as 0.01, then the corresponding reflectivity, it will be 0.99. Similarly, for the rough or hard packed dirt, the effective emissivity is 1. So, reflectivity will be 0. So, if any signal falls on bare metal, it is going to reflect almost all of them, but if it falls on hard packed dirt, it will absorb all of them. So, if we do not have a secondary source to illuminate this bare metal or hard packed dirt, so in that case, due to the black body radiation, we will expect more radiation from the dirt, hard packed dirt, and less radiation from the metal. So, in case of we do not have, let us say, any secondary source, and in that case, if we do passive imaging, so metal objects, it appears as black color, and since this dirt is emitting more power, so it will appear as white in my picture. So, next let us see what advantage we have at millimeter wave frequencies, particularly for this passive imaging. So, this is showing the black body radiation, which is a function of frequency and temperature. So, you can see left hand side, we have spectral radiance per unit wavelength, and along x axis we are plotting the frequency. So, sun, it has a surface temperature of 6000 Kelvin. So, the highest spectral density is at it corresponds to the yellow line of optical wavelength, and if I increase the frequency for the sun, it left hand side, so it decreases, and right hand side, if I decrease the frequency, it also decreases, and the peak value where it will appear, it depends on the temperature. Now, if I consider any ground based object, let us say the temperature is 300 Kelvin. So, in that case, the peak value, as you see, it appears approximately in infrared frequency range. So, now if I go to right hand side at lower frequency, first sub-millimeter wave, then the millimeter wave frequency range, the efficiency, the emission, it decreases. So, if I compare typical values at infrared and at millimeter wave frequencies, at millimeter wave frequencies, this is approximately 10 to the power 7 times less than that at infrared frequency. So, that means if we design any passive imager, we have to keep in mind that we are going to have a spectral density which is much smaller. So, as high as 10 to the power 7 compared to what available at infrared frequency range, but we have some other advantages at millimeter wave frequencies. So, first of all, millimeter wave receiver is much sensitive compared to infrared receiver. How sensitive? Approximately 10 to the power 5 times, and not only that, you can increase the received power by simply increasing your aperture area, receiving aperture. So, you can use arrays and antenna arrays, or you can use a big size parabolic reflector to receive more power. So, then at the end of the day, you have a comparable system at millimeter wave frequency, but millimeter wave frequency is some special advantage which we do not have at infrared. What is that advantage? Let us see. So, even though we have seen that millimeter wave frequency, it is attenuated by atmosphere or weather, typical weather conditions like fog, dust storm and rain, but if I compare that attenuation with what we have at infrared frequency, it is much less at millimeter wave frequencies. Let us take one example. Let us say we are measuring the same quantity under foggy condition, typical visibility is 50 meter, and in that case you can see this right hand side plot, radiation through fog. So, for the infrared in clear sky condition, it was approximately 10 to the power 7 times, and now even at 10 to the power minus 10 we do not have anything, but at millimeter wave frequencies it of course it decreases attenuation, we have some finite attenuation due to fog, but still maybe just 10 dB per kilometer. So, if I can design any imaging system at millimeter wave frequencies, we can call it all weather imaging system. So, it is very popular, that is why for defense application. So, you can take imaging even under heavy rain, even under heavy fog, dust storm and even in sandstorm condition. So, all weather imaging is possible at millimeter wave frequencies, but when we go for imaging, we have to keep in mind that we can use only some windows, because we have some attenuation band. So, this is typical plot of temperature of atmosphere versus frequency. So, since at 60 gigahertz oxygen molecule it absorbs power due to resonances. So, at 60 gigahertz atmospheric temperature will be very high. So, similarly at 118 gigahertz we have one more attenuation band, again due to the oxygen molecule, and near 180 gigahertz we have one more due to H2O molecule. So, for passive imaging only some windows are available, we have to utilize those windows. So, here for example 30 to 50 gigahertz or 70 to 100 gigahertz or 130 to 150 gigahertz, we can use these windows for any radiometric measurement or for passive imaging. Some more applications. Weapon system. So, it is a non-lethal weapon system called active denial systems or ADS. You can see it is mounted on a truck, military truck. So, what it does? It basically generates high intensity millimeter wave signal, and typically it uses a frequency for which the wavelength is 3 millimeter, and when it falls on any person, they will have a burning sensation, but due to the size of this system, it did not become popular. Some other popular applications, security screening. So, millimeter wave, it can pass through clothing and other organic materials. So, that is why, but it does not pass through our skin and muscle. So, that is why we can use active millimeter wave imaging to find out if anybody is carrying any weapons or any other things, and it is already in use in airport. So, for example, this is you can see this photograph. So, what it does? So, they will ask you to enter one chamber as shown in this figure, and we have arrays of millimeter wave antennas as can be seen here. So, it generates millimeter wave signal, and we have another arrays of antennas which actually receive that millimeter wave signal, and it can turn to form the complete image. And since millimeter wave it can pass through cloth, but not through skin, so it can show picture, and it can show if there is any hidden weapons is there or not. So, at present scientists are trying for long distance millimeter wave imaging. So, once it is possible, most probably you do not have to enter this chamber in airport. So, it can the target is 50 meter. So, it will be able to scan a large people without asking them to enter that chamber, and without their knowledge it will be able to scan for any hidden weapons. And less popular application in Russia, it is used for medical applications to treat some diseases. Another popular application, collision avoidance radar, it is already there. So, typically it uses 77 gigahertz spectrum. So, we have one FMCW radar installed inside the car, which constantly monitor the traffic in front of this and just beside it, and when it is within a distance, we call it collision warning distance, then it will warn you by giving some beep sound. So, we have seen that already we have different applications, and to give you some ideas about the frequency range and the power already being used for different satellite based applications, here is a chart. So, for example, for cloud radar, it is already in use. Typical frequency it's operate at 35 gigahertz, and the average power 10 to 100 watt, and antenna size it use 1 to 3 meter. FMCW radar frequency 95 gigahertz. In one type of system it's working, its transmitting power is 0.1 to 15 watt, and antenna size 0.3 to 2 meter, and in second category it's 0.1 to 1 watt, and the antenna typical diameter is 1 meter. So, we have seen that already there are many millimeter wave systems it's being used, and now scientists are trying for different other applications at millimeter wave frequencies, typically for wireless systems, but till now it is popular mainly in defense applications. Why? Because of its cost. So, to minimize cost or to reduce it, we have to go for some new technology, typically silicon germanium or CMOS by CMOS technology, because whatever millimeter systems I was showing till now, they are based on gallium arsenide or other group 3 group 5 materials, which are very expensive. Only military can afford this price. So, if we really want for consumer applications, so we have to first find out a solution, so that it can be fabricated by using a cheaper process like CMOS and BiCMOS. And I will show you some of the examples. So, already scientists they fabricated some of these devices, and in silicon and germanium technology, and it is already there in market. So, in near future we can expect that in consumer applications, so we will be using millimeter wave components and millimeter wave systems. So, next let us discuss some other things. So, different guiding structures. So, for this wireless medium, we send millimeter wave signal from transmitter to receiver without using any wire or any guiding medium. But when we design the millimeter wave system, let us say a transmitting system or a receiving system, so inside we have many components. For example, for the transmitter we have the source, then we will be having filters, couplers, and low noise amplifier, power amplifier. So, different components in a single system. So, we have to connect them. So, for this connection we need some wave guiding structures. So, then what are the popular wave guiding structures? Those we use at millimeter wave frequencies. So, we learn these popular wave guiding structures in this class. So, some of them are listed here. So, hollow metal waveguide, it is very popular and it is bulky, but the main advantage is that its attenuation is minimum among all available solutions, and also it has highest power handling capability. So, that is why even though it is bulky and expensive, it is in use for millimeter wave applications. Then the planar transmission lines. So, at microwave frequencies we use microstrip line, CPW line. At millimeter wave frequencies they are lossy, but for chip to chip communication we can still use it when its typical distance is not more than a few millimeter. We also have some quasi planar transmission line like fin line. Then we have dielectric integrated guides like non-radiative dielectric guide, we call it NRD, image guide, insular image guide. So, different forms of dielectric integrated guides, and then H and group guide structures. So, H and group guide structures nowadays people do not use it because it has some other problems. So, here we can see some typical guiding structures. The first one is circular and rectangular waveguides. So, it looks like hollow metallic pipe, you can see inside we have air, and this is a microstrip line. This is actually showing the cross section of this transmission line system. So, this orange color it is showing the metallic part, and this blue color it is one type of insulator, we call it dielectric. It is showing its dielectric constant is epsilon r, and we will see later that at millimeter wave frequencies we can't use metal for power transmission. At 50 hertz we use twisted wire for power transmission. At megahertz frequencies we use two wire parallel two wire system. At gigahertz or microwave frequencies you might have seen rectangular waveguide in your lab or coaxial cables, but at millimeter wave frequencies coaxial cables and this two wire system or twisted wire we can't use it, it becomes very lossy. So, we use typical dielectric material which actually supports this energy propagation, and metals we will be using just to guide this electromagnetic wave, so that this electromagnetic signal is confined inside the dielectric material. So, before starting the next section, we will first learn some terms, because we will be frequently using those terms. So, we will take again a short break, then we will first learn those terms. Thank you.